Welcome to the Introduction to Calculus. I'm Mr. Stark. We're on lesson 1B, derivatives. In the previous lesson, we talked about average velocity and instantaneous velocity. Well, it's helpful to know that average velocity relates to the secant line, which is the line that passes through the position function twice. So we could use those 2 points to calculate slope, which is the average rate of change, and when we're using the position function, it's called average velocity. It's also helpful to know that instantaneous velocity relates to the tangent line, which is the line that touches the position function at a point of interest. If we know the slope of the tangent line, then we have found the slope of the curve at that point of interest. So let's learn more about the tangent line. Writing the equation of a tangent line is a common thing we do in calculus. There are 3 steps. First, calculate slope. Second, find the y value. And these 2 steps could be interchanged. Step 3, write the equation in point-slope form. And that's key because that equation tells us the point of interest and the slope. Super helpful, super unique name. So for example, we have f of x equals 3x squared minus 5. Let's say we wanted to find the slope of that curve, which is a parabola, at x equals 1. Okay, we could have chosen 2 or negative 5 or whatever. So we're going to take the limit as x approaches 1 of the difference quotient. And really the difference quotient could be seen as a variety of things. It could just be delta y over delta x. But I have 2 algebraic formulas I'll show you in a moment. But let's say we go through that process and we find that the slope is 6. Great. Step 2, find the y value. And we do that by just plugging in 1. And we want to know that this value is different than what we just did in the first step. So keeping consistent with our notation and knowing what the numbers mean. So plug in 1 into x squared, which is 1, times 3, which is 3, minus 5, which is negative 2. So the y value is negative 2. Then write the equation. So that looks like y minus something, the y value, which is negative 2, and I use parentheses, equals 6 times x minus 1. And we'd be inclined to solve that, but we don't need to. We want to leave it in point-slope form so we could see the point and see the slope. And that's it. Let's talk about the derivative. There are 2 ways to think about it. The first one is derivative at a point, which is slope at a point, finding the slope of the tangent line and getting a numerical answer. And there are 2 formulas that we could use to define it. So let's do that. The derivative of the function f at x equals a, and this is already written, denoted by f apostrophe parentheses a, and read f prime of a is. So here it is, the first formula. The limit as x approaches a of slope, f of x minus f of a over x minus a. That's all equal to, as long as we do it correctly, the limit as h approaches 0, a new variable, don't freak out, of f of a plus h minus f of a divided by h. That's called the difference quotient. And notice that if you plug in 0 right away for h, you get undefined. That's why the whole algebraic process is important. So here goes. We have this function as an example, 2x plus 4. And we're trying to find f prime of 3, which based on our definition we just went through, is the derivative of the function f at x equals 3. That's our point of interest. Here's how you do it. And you have to write kind of small if you're using my booklet. F apostrophe parentheses 3, so f prime of 3, is equal to the limit as h approaches 0, let's use the difference quotient 1, of f of 3 plus h minus f of 3, all divided by h. Notice that that notation is saying, hey you, plug in 3 plus h into f. And hey you, plug in 3 into f. So let's do that next. The limit as h approaches 0 is equal to 2 times 3 plus h plus 4, minus some other stuff that I'll tell you in a moment. But notice that 2 times 3 plus h plus 4 is plugging in 3 plus h for x. Then we subtract f of 3, which is simply 3 plugged in for x. So it's 2 times 3 plus 4. All of that divided by h. Again, just notice that the 3 plus h and the 3 are just being plugged in to the function f as x. If we simplify the numerator, we'll get the limit as h approaches 0 in front, 6 plus 2h plus 4 minus 10. So I distributed the 2, I left the 4 there, and I noticed that 2 times 3 plus 4 is 10, divided by h. The next step is to rewrite the limit as h approaches 0, and notice now that 6 plus 4 minus 10 is 0, so we get 2h over h. It's very common that we end up getting a quotient that involves an h in the numerator and an h in the denominator, so that we could divide that out. What we are doing in that moment really is dividing out the issue that we experienced with 0 divided by 0 in the previous video. Basically, the tangent problem that we're solving right now. So that's equal to the limit as h approaches 0 of 2, or 2 divided by 1. Well, there's no place to plug in the h. There's no h anywhere. So the limit as h approaches 0 of 2 is just 2. Some other ones get more complicated, and we'll see a different example soon, but just know that that slope that we just found is a few things. It's the derivative at a point, so 2 is the derivative at x equals 3. It's also the slope of the tangent line at x equals 3, and it's really just the slope of the entire function, because it's always 2. The second way that we could think about the derivative is the derivative function. It's a function that tells us the slope of another function at any x value. Wow, that's pretty great. Here it is. If y equals f of x, then the derivative of the function f with respect to x is the function f prime, whose value at x is the limit as h approaches 0 of f of x plus h minus f of x divided by h. Hey, that looks familiar. That's the same difference quotient for the derivative at a point, except we're using x values instead of a values, meaning we'll use the x variable and not numbers. So for example, find f prime of x if f of x is 2x squared. It's basically saying find the derivative function if f of x is 2x squared. You know the regular function. So the limit as h approaches 0 of 2 times x plus h squared minus 2x squared over x. Notice that we're taking the x plus h and we're plugging it into x into the function. Okay, we did that same thing before. That's equal to the limit as h approaches 0, and I'm expanding out x plus h. So here's where the algebra comes in. 2 times x squared plus 2xh plus h squared. And that could be found by multiplying with a Punnett square, or just doing FOIL method in your head, or even on paper. Minus 2x squared divided by h. So the next line is the limit as h approaches 0 still, but then I distribute the 2. Okay, we could do that fairly quickly. And that's equal to, and notice what happens here, the 2x squared at the beginning and the negative 2x squared at the end become 0. So we end up with 4xh plus h squared divided by h. Again, notice that there's an h that's common among all of the terms in the expression. So with the one with 2x plus 4, we had 2h over h. Here we have just an h in each one. So if we factor out an h, we end up getting the limit as h approaches 0 of 4x plus h. No denominator. And so again, we've like divided out the issue that we have with the tangent problem. So now when h approaches 0, think about if h is like 100, you'd get 4x plus 100. But if h is 0, that's taking the 2 points that are part of a secant line and making them closer together so that the tangent line, it's just the line that touches the curve at the point of interest. Right now we don't know that point of interest, so we have a general expression which is 4x. So f prime of x equals 4x, and that is the derivative of 2x squared. Well, that's the end of topic 1, the tangent problem. In Calc AB, the tangent problem and derivatives account for almost half of the course. In Calc BC, approximately a quarter. Some good stuff there. And Calc BC goes quite fast. If you have any questions or comments, please feel free to add them below. And thank you so much for watching.